In this lecture, we'll be discussing simple harmonic motion. So far in the course, we've studied linear motion, circular motion, rotational motion, which is a combination of both linear and circular, and the last type of motion that we are going to study is vibratory motion. Vibratory motion is widespread in nature. Vibrations occur both on the small and on the large scale. On the small scale, example is vibrating atoms, and on the large scale is vibrations that we observe in our daily lives, strings of a musical instrument, shock absorbers on our car, etc. What characterizes a vibratory motion is a periodic nature to the displacement of an object. That is, the displacement, so that we can call this S. Displacement S over time repeats itself, and this period over which the position of the object is back to where it was is called period of the oscillation rather, T. The units for T being seconds, of course, in the SI units. The period is defined as time interval over which the displacement of the object is back to where it was. So it's the period as a time interval from peak to peak, or crest to crest. I can't show it there on this drawing, or the zero crossing to this zero crossing right there. In zero crossing, you have to be careful, of course. We have to choose the identical position. And in this zero crossing here, the object is moving in the negative direction, so the period is defined from this zero crossing to this zero crossing, where the object is moving in the negative direction again. So period of the object T is the time interval over which the displacement is back to where it was, and 1 over T is called the frequency of oscillation. The frequency of oscillation, the units for which are hertz, is the inverse of the period. Hertz, or seconds to the minus 1. In 1822, a French mathematician, physicist by the name of Joseph Fourier, who happened to be one of Napoleon's army engineers, proposed the following theorem. His theorem put forward the concept that if we have a periodic oscillation, a periodic motion, an oscillation, a vibratory motion. Now this vibratory motion can be simple, or one that is shown by that black wavy line, so convoluted vibration, or for that matter any other type of vibration. So this here is also vibratory motion, a periodic motion. If we have a motion where we know its period T, notice that in all these cases the motion repeats itself over a certain period T. This means that the excuse me, this means that the oscillations have a frequency F. Okay, so if we know that a motion is characterized by frequency F, then we can describe that motion in terms of series um, of simple harmonic oscillations of frequencies f1, so that's f, plus second harmonic, plus third harmonic, plus fourth harmonic, etc. So by giving the correct weighting factors, so we can call this C0 or C1 rather, C2, C3, C4, you can generate this function, the original function that we had in which has a frequency f. An example that I've generated here using 3 sine waves. This has a frequency 1f, frequency twice that frequency 2f, and 3f. So by simply adding 1f to 2f, you generate what is shown on the top right hand graph, and by adding all three, so this is 1f plus 2f plus 3f, we get what is shown in the lower right hand graph. So excuse me, I'm suffering from rather serious cold this weekend. So you see that by correctly weighing each harmonic and adding the harmonics together, we can generate pretty much any function which has a periodicity of fundamental frequency f. See the period for the function here is shown there, so here we also have the same period, and etc. So this concept of simple harmonic oscillator really was put forward by Fourier, and its importance is that if you can describe a simple harmonic oscillator, these are simple harmonic oscillators of frequency 1f, 2f, 3f, etc. Then by adding series sum of these simple harmonic oscillations, we can mathematically describe any oscillatory motion which has a frequency 1f or f. So what is this simple harmonic oscillator? What's the mathematical description for it? Well, there are two ways to define simple harmonic motion. There is the kinematic way, or the dynamics. So we can either use kinematics or dynamics to describe a simple harmonic oscillation. The kinematics technique is rather straightforward. So using kinematics, we can describe a simple harmonic oscillator, a simple harmonic motion, by the way it behaves. So how a simple harmonic oscillator moves mimics the projection of an object. Here, let's say we have an object that is moving around in a circular path. So if this object moves in some time delta t over to this position, so this is our initial position, this is our final position, the angular displacement it goes through, let's call that theta. Excuse me. Then the projection of the position of the object along a diagonal line through the circular path that is moving in, it gives you a simple harmonic motion. So if the particle is here, then we essentially follow the position of the particle, the object, along this diagonal. It's basically moving back and forth, back and forth. As you can imagine, it will speed up. Oops, I'm sorry. It will speed up in the areas closer to the center of rotation, and it will be moving more slowly at the extremities. So mathematically you see that this position, if I call this the x-axis, then the position that the object is at, let's call this x. X is simply given by a cosine theta, where theta is the angle that we defined here, and a is the radius of the circle. So a cosine theta is of course this position right there. So if the object is in this position, then its projection along the diagonal line is here, and this distance here is of course x, which is given by a cosine theta. Now theta is related to the angular velocity that the object has, omega, through the kinematic equation omega t plus phi naught, where t is the time that it takes for the object to undergo through that angular displacement, and phi naught is what we call the phase constant, which defines the position of the object at t equals 0 seconds. So rather than our object starting at along the diagonal at t equals 0, what if the object had started, for example, here? If the object had started there, actually let me do a new drawing here. So that's another circular path. This is our reference diagonal x, and let's say the object starts here in this position, so that's our initial position, and then it moves to this final position here. So our angular displacement over time t is our theta, the angle that I've shown in the drawing. So theta is equal to omega, that's the angular displacement, that's delta theta here, I'm sorry. This is our delta theta. Delta theta is omega t, but the angular position of the object, theta, is equal to our delta theta so theta is equal to angular displacement plus the initial position of the object, which is phi naught. So phi naught is the initial position of the object, delta theta is the angular displacement. So initial position plus angular displacement gives us our final position, of course. So in general terms, theta is equal to omega t plus cosine of phi naught. Therefore, the kinematic equation describing simple harmonic oscillation is given by x is equal to a cosine of omega t plus phi naught, where phi naught, as we just covered, is the phase constant, describes the position of the object at t equals 0 seconds. Omega is the angular frequency of the oscillation, and omega is equal to 2 pi f, where f is the 1 over period of the oscillation, and a is the amplitude of oscillation. So the larger a we have, of course, the larger the amplitude of the oscillation is going to be. Okay, the larger a gives us a bigger amplitude of oscillation, etc. Now taking a derivative of position with respect to time, we end up with velocity, of course, and the derivative would be a minus a omega sine of omega t plus phi naught. So this is the velocity equation for our simple harmonic oscillator, and taking yet another derivative, we obtain the acceleration function, which is minus a omega squared cosine of omega t plus phi naught, which is equal to minus omega squared x, because a cosine of omega t plus phi naught is equal to x. So the characteristic equation describing simple harmonic oscillation using the kinematic technique we show is that ax, the acceleration of the object, is equal to is given by a constant omega squared negative of a constant times the position. So using kinematic techniques, we can describe simple harmonic oscillation as the projection along a diagonal of an object moving around in a circular path, and that projection, of course, is given by the x equals a cosine of omega t plus phi naught, where phi naught is the phase constant of the object describing its initial condition at t equals 0 seconds. Now, a second way to describe simple harmonic motion is using dynamics arguments. So using dynamics, which is the argument of how, not how, but why do objects move in the way that they do. The definition of a simple harmonic oscillation, we can start by saying that we need to have a restoring force acting on the object for it to undergo simple harmonic oscillation. What we mean by a restoring force is that our force must be proportional to the displacement from some equilibrium position, and it will need to be pointing towards that equilibrium position, therefore the negative sign. For example, if this is our s-axis, let us call our equilibrium position S0 to be here, then the force that the object would experience when it's in this position, right there, would be proportional to its displacement from the equilibrium position, and it will be, you draw the force in red, it will be pointing towards the equilibrium position. So our Fs here is negative, pointing towards the equilibrium. When the object is further out along the s-axis, then Fs is still negative and even bigger than it was in the previous case, because the displacement is now greater. Now when the object is on this side, then Fs is positive. So when the displacement is negative, excuse me, when the displacement is negative, the force acting on the object is positive. Remember, the force in a restoring force always points towards the equilibrium position, and it's proportional to the displacement. And such an example of such a force is, of course, force of a spring that in spring exerts on an object which is attached to it. So if our string is along the horizontal attached to a wall, here's our object M. If we say that this is the equilibrium position x naught, then when the object stretches the spring, spring force is in the negative direction, and when the object is compressing the spring force is going to be in the positive direction. And as we saw, the spring force is given by Hooke's law. It's proportional to the displacement itself, and the constant of proportionality was the spring constant of the spring in use. So if we have a restoring force acting on an object, then that will result in simple harmonic motion for the object. Another way to describe this is, well, force is equal to mass times acceleration. This notation double dot simply means the second derivative of position with respect to time, d2s dt squared. So m d2s dt squared is equal to a negative of a constant times position, which that's simply Newton's law, which means that acceleration of the object, or d2s dt squared, simply equal to minus c over m s, where c over m is a constant, and as we saw up here when we did the kinematic argument, acceleration of the simple harmonic oscillation is equal to minus omega squared x. So this form agrees with what we obtained using kinematic argument, which gives us as is equal to minus omega squared s. Omega being the angular frequency of the oscillatory object, oscillatory motion. Now, the equation of this type is a differential, second order differential equation. So to find a solution for this equation, there are different techniques that can be used. One technique is simply guess a solution and then try it out and see if it works. So if we guess that a solution of the form S is equal to A cos omega t plus phi naught might be a solution, let's give that a try. Substituting S equals A cosine of omega t, actually just differentiating with respect to time, we end up with minus omega A sine omega t plus phi naught, and that's our second derivative, would be minus omega squared A cosine omega t phi naught, and A cosine omega t is of course S, as we defined up here, which gives us d2s dt squared is minus omega squared S. Therefore, that's of the same of the form that we said as our motion needs to be. Therefore, S as given by A cosine omega t plus phi naught is a solution to our second order differential equation that we have here, which leads us to deduce that a simple harmonic oscillator would need to follow this displacement equation, cosine of omega t plus phi naught. Now we drive the same equation that we had, but using dynamics analysis rather than a kinematics analysis. So in the kinematics analysis, we simply described how the object, a simple harmonic oscillator, moves, and we said that it moves according to the projection of its position along the diagonal of the circular path. In the dynamics analysis, we argued that there has to be a restoring force involved, and we arrived at the same expression for the simple harmonic oscillator. Now in the case of the spring force, the restoring force is given by Fx is equal to minus kx. So the acceleration d2x dt squared is minus k over mx. But we said that the simple harmonic oscillator is to follow this equation, d2x dt squared is minus omega squared x, which gives us omega is equal to square root of k over m, which means that if you have mass attached to a spring which has a spring constant k, and we stretch the spring and stretch the string and let go, the mass on the spring will oscillate in a simple harmonic manner in between plus a and minus a with an angular frequency of k over m. So a is the amplitude of oscillation, right? And the square root of k over m will be the angular frequency of the oscillation. It's important to note that the frequency of oscillation is independent of amplitude a, so it doesn't matter how much we what disturbance we cause to the mass on the spring, it will always oscillate at the same frequency. Important thing to remember though is that this restoring force equation must be followed, and as I had mentioned previously when we studied Hooke's law, is that strictly speaking, Hooke's law is not a physical law because it's only valid over a small range. The displacement from equilibrium must not exceed 10% of 10% of the spring's total length. Otherwise, this linear relationship will not be followed. And when that relationship is not followed, we no longer have a simple harmonic oscillator. Excuse me. We'll have an aharmonic oscillation. The other important thing to note, as I mentioned, is that the frequency of oscillation is independent of amplitude. It only depends on spring constant and mass. Notice that if we have a larger k, which means a stiffer spring, then the oscillation will be of a greater frequency. And if we have a larger mass, the oscillation frequency will reduce, get smaller, etc. So important relationship to note. Now we also say that to have a simple harmonic oscillation, we don't necessarily need a spring. Any system where we have a restoring force at work will lead to simple harmonic motion. An example of a system not involving a spring but where a restoring force is at work is of course a pendulum. Pendulum given by mass m, the mass of the bob is m, the length of the pendulum is L, let's say. And when this is our equilibrium position, and when the pendulum swings out to, let's say, this position at the right hand side, then the position of the bob of the mass m is given by along the arc length s, and the force acting on the bob when it's in this position is its magnitude is mg sine theta, where theta is the angle shown in the drawing, and of course mg is the weight of the bob. But because mg sine theta is pointing towards the equilibrium position, then we know it's a negative mg sine theta. So the force on the bob is equal to mg I'm sorry, not there. The force on the bob is given by minus mg sine theta, and if angle theta is small than sine theta, we can use this approximation, as sine theta is approximately equal to theta. This is provided we work in radians, of course. So for small theta, sine theta is equal to theta, which and then also using the relationship S is equal to L theta. This is arc length is equal to the radius of the circular path times angular displacement. We can rewrite this equation in this form, which is minus mg s over L. Okay, now this Fs, the force on the bob, is given by minus mg s over L. But force on our object is, according to Newton's equation, is simply mass times acceleration, as. So mg over ls is equal to m d2s dt squared, or mas. Now you notice that mass cancels from both sides, and we end up with this relationship here. d2s dt squared is equal to minus g over L. This equation once again is of the form d2x dt squared is equal to minus omega squared x, which is one of a simple harmonic oscillator. So which means that for the case of a pendulum, the pendulum will describe simple harmonic motion whose frequency is given by the square root of g over L. So this term here is our omega squared. Okay, this is true provided theta is small. So if you swing the pendulum out too far, then it will not follow simple harmonic oscillation. So you need to be within 10-15 degrees for the pendulum to obey simple harmonic motion. And all these and also do notice that this frequency of oscillation is independent of mass. So no matter how big of a bob one has, the period of the oscillation will depend only on exertion due to gravity and the length of the pendulum, which is good news for people designing grandfather clocks. They can design the grandfather clock with pretty much any bob, and only tune it by adjusting the length of the pendulum. Now, we said that if we have equation of the form d2x dt squared is minus omega squared x, we have simple harmonic oscillation. Multiply both sides by m, and we end up with force is given by minus cx, where c is a constant. We showed that that constant is equal to omega squared. Now what if there is other forces involved in our system? For example, if we were to take our pendulum, strictly speaking, the pendulum moves in air, so there is some air resistance involved. So we can now add yet another term to our equation. So the force is not simply equal to minus cx, but there's yet another form, another force acting on the bob, and this force may depend on position, of course time. So in the case of the pendulum moving in air, we're talking about air resistance. back in chapter, forget, 3 or 4, we argued that the drag force is proportional to velocity squared, but that was true for if the velocity were large. Moving pendulum in air, the velocity isn't large, and for small v, one can show that the air resistance force, which we'll just simply call F, is proportional to the velocity of the bob through air. Now, v is dx dt, so we can, in the case of a pendulum moving in air, this function, that would resist the motion, we can show by a constant b times dx dt. So this is the air resistance force on the pendulum. So our equation now becomes d2x dt squared is minus c over mx minus bm dx dt, where c over m is once again is the gives us the square of the angular frequency of oscillation if there's no air resistance, and this b over m is damping that occurs, the coefficient due to the air resistance. In fact, constant b is called the damping factor or damping constant. So the larger b is, the larger the resistive force is going to be on our motion. So if you were to take the pendulum and put it in a big ball of water and start swinging the pendulum, of course it will move at a much slower frequency than it would have if it were in air, for example. Now this second order differential equation is, we have the second order term, the first order term, of course the zeroth order term. You can once again find a solution for this second order differential equation using once again the guessing technique, and a possible solution is of this form, which, as you can see, does describe a simple harmonic oscillation. So xt is given by a cosine omega t plus phi naught. Once again, omega naught is our phase constant. However, both a and omega, again a is the amplitude of oscillation and omega is the frequency of oscillation, are not constants anymore. If we had, in the case of no air resistance, a and omega were simply constants. Amplitude of oscillation remained constant, and omega was the frequency of oscillation. Where a, in the case of a damped oscillation, is now given by this term, a naught times exponential of minus b over 2m over t, where a naught is the amplitude of oscillation at t equals 0, and this exponential term describes how the amplitude diminishes over time. Before I describe the graph I have here, I should say that omega is now the angular frequency of oscillation, which is actually constant. So slip of the tongue there. Omega is constant. However, its value is smaller than what it would have been with no air resistance. So omega naught is the case where this resistive force F is 0, and if we have air resistance to the motion of the bob through on the pendulum, then our new angular frequency is smaller by this amount, which depends of course on the damping constant B and the mass of the bob, etc. So when F equals naught, of course omega is equal to omega naught. But if we have some kind of air resistance, i.e. B is not zero, then omega will be less than the natural oscillation angular frequency of the natural angular frequency of the object. So this amplitude term, let me get rid of these lines. If there is no air resistance, then the amplitude over time remains constant, of course, as shown in this graph here. However, when there is resistance, then the amplitude will have a 1 over t e exponential decay term to it, and the frequency of oscillation will be slightly less than the case with no resistance. Okay, so eventually the amplitude will get smaller and smaller, closer to zero. Important thing to note though is that the equation, the position versus time equation for an oscillator with damping still describes a simple harmonic motion, but one where the amplitude has an exponential decay term to it. Now, these equations describing position, velocity, and acceleration, which we derived by differentiating once and twice, are the kinematic equations of motion for a simple harmonic oscillator, or simple harmonic motion kinematic equations. And at t equals 0, we see that x naught is given by a cosine of phi naught. V naught, which is the velocity of the mass at t equals 0, is minus a omega sine phi naught, and the acceleration of the mass at t equals 0 is minus a omega squared cosine of phi naught. So that's why we say the phi naught describes the condition of the oscillator. So describes condition of oscillator at t equals 0 seconds as phase constant. The other thing to note is that by simply looking at the kinematic equations, we can deduce that maximum displacement is equal to a, because the maximum value that this function can take is 1, of course, a trig function, and the maximum value that the velocity function can have is a omega, using the same argument for the maximum value of the sine function here, and the maximum value of the acceleration is a omega squared. So once again, excuse me, these are important, well, handy relationships to remember or to have on your equation sheet. And of course, a is amplitude, omega is angular frequency, and phi naught is phase constant. Let's now take a look at energy in simple harmonic motion. We said that the position versus time for a simple harmonic oscillator is given by a cosine omega t plus phi naught, and the velocity is minus a omega sine omega t plus phi naught. Well, let's make use of the velocity term to determine the kinetic energy of a simple harmonic oscillator. Kinetic energy, which is defined as 1/2 of mass times velocity squared. Plug in this function for v, velocity, and you can show that the kinetic energy of a simple harmonic oscillator is simply given by this equation here. Potential energy is position dependent, so we're going to make use of the position equation, and we had seen back in chapter 10, I believe, that the potential energy of an object due to is equal to the negative of the work done by the force that causes that potential energy. So potential energy was the negative of the work done, which causes that potential energy, and the definition of work being the integral of the force that brings about that force, that potential energy over displacement. So that's the definition for work that we had in chapter 11. So this part is from chapter 10, this part is from chapter 11. The negative sign is from right here. And we said that this force for a simple harmonic motion is equal to minus omega squared x. Those are as we saw up there. So simply substitute that in and evaluate this integral. It's a simple integral to evaluate, and one ends up with the potential energy in simple harmonic oscillation is being given by 1/2 of mass times omega squared x squared, which you can now go ahead and substitute in the expression for x, and you end up with this lovely equation down here, which is minus 1/2 m omega squared and this is our x squared essentially. Now it is interesting to note that if you take the expression for kinetic energy and the expression for potential energy and add them up, because sine squared plus cosine squared is equal to 1, then you would end up with K plus U, which we said is the total mechanical energy of the object, is given by 1/2 of ma squared omega squared. Okay. Okay, I paused the lecture briefly because I just realized that I'd forgotten to include a mass term here, because minus omega squared x is the acceleration ax, so we need to multiply it by mass to get f, but in my substitution I had actually gone ahead and put that in, so the integral is correct. And the other thing which kind of caught my eye, but that's what I want to double check, is that I've included too many omega squareds. X squared is a squared cosine omega t plus phi naught, because x is equal to a cosine of omega t plus phi naught. But this is correct, of course. So total mechanical energy of the oscillator is kinetic energy plus potential energy, which is 1/2 of a squared, 1/2 of mass times a squared times omega squared. So if we go ahead and write the total mechanical energy as 1/2 of ma squared omega squared, notice that both these values are constants for a simple harmonic oscillator, which means that the mechanical energy of a simple harmonic oscillator remains constant. That's that red line here, and the kinetic energy follows the blue curve. So when the velocity at equilibrium, let's say that the center here, the origin is the equilibrium position. This position is plus A, and this is the negative displacement. And the velocity of the oscillator at either minus A or plus A is 0, of course. Therefore, the kinetic energy, which is that blue curve, is 0 at the two extreme positions, and it's maximum at the center position. Now, potential energy depends on position, so at the origin it's 0, and at either end it's maximum. And those maximum values are of course equal to the total mechanical energy that the object has. By the way, in this equation for omega, if you're dealing with a mass on a spring, then omega is given by square root of k over m, and if you're dealing with a pendulum, it's given by square root of g over l, or later on, if you encounter different type of a different force involved, then you need to analyze your system and decide what omega is given by for the particular system that you're working with. But this equation is a generic equation that is true irrespective of the form of restoring force involved. Now, if we were to ask ourselves when does potential energy equal kinetic energy? So to answer this question in terms of position we can answer this question in terms of position or velocity. So let's answer it in terms of velocity. If you're going, so let's say that we're interested to find out when does kinetic energy and potential energy equal, at what velocity, what's the velocity of the object when of a simple harmonic oscillator when its potential and kinetic energies are equal. Well, this is our generic expression, so we can write that either in terms of 2u or 2k, since u equals k. If we are interested in velocity and the answer in terms of velocity, then of course it's the kinetic energy relationship we're going to use. We know that total energy is equal to 1/2 of mv max squared. That's because in a curve here that we had up here, total energy is the maximum kinetic energy that the object has. Now that's equal to 2k, and 2k is simply 2 times 1/2 of mv squared. Canceling out m's and halves, we end up with v squared max is equal to 2v squared, which gives us velocity of the object must equal its maximum velocity divided by root 2 when kinetic and potential energies are equal. Now, if you're interested in figuring out this answer for position, so at what position does kinetic energy and potential energy equal, then of course, because after position we use the 2u, the potential energy expression. Now the maximum kinetic energy, maximum potential energy is given by 1/2 of ka squared, which is equal to the total energy of the system. That once again is from our curve up here. So in this position and in this position, the two extreme points, potential energy max is equal to total energy, and potential energy max, U max, simply 1/2 of in a system with a spring is 1/2 of ka squared, of course. So that's why I say you need to know what system you're dealing with to come up with an answer in terms of factors that mean something. My screen is frozen. I apologize for the delay, but I cannot scroll down. Let me pause the presentation and see what's going wrong here. Alright, I think the screen released me, so I'm back. So what we have is 1/2 of Ka squared is equal to 2u, where u is 1/2 of Kx squared. And so you can see that at x is equal to amplitude over root 2, the two energies, the kinetic energy equals the potential energy. Now of course you can use this line of argument to figure out, for example, when does kinetic energy equal 1/2 of u. Simply write your total energy as u plus half of u, where half of u is k. And so E is equal to 3 over 2u. And since we're interested at what position does kinetic energy equal 1/2 of potential energy, use the potential energy relationship, which total energy is 1/2 of Ka squared, and u of course is 1/2 of Kx squared, and 3 over 2 is the factor we just figured out from above. So at x is equal to a over square root of 3 over 2, kinetic energy has 1/2 of the value of the potential energy. So you can pretty much find position or the velocity of the object for any ratio of kinetic to potential energy that you're interested in. The screen is giving me trouble again. I apologize. Alright. Now, last thing I want to mention is that the total energy of the system, mechanical energy of the system, depends on the square of the amplitude, a squared. And when we have our generic position versus time equation for our simple harmonic oscillator up here, and if there is no damping involved, of course amplitude is constant, which means that our energy is given by this blue line there, is constant over time. But if there is damping involved, then remember that damping is with damping, amplitude depends on a naught, that's the original amplitude, and then has an exponential decay term to it. So a squared would then be equal to would be proportional to this decay term here. So it will be given by this green line with an exponential decay term with the damping factor b as the argument. So the energy of a simple harmonic oscillator with damping, of course, it starts at the initial value, but then decays exponentially over time as prescribed by this exponential decay term. What I will be doing tomorrow is publish yet another lecture working out examples on simple harmonic motion, pretty much going over the homework problems that I've assigned on this chapter.